Okay, welcome everybody. So we are going to continue working with changing coordinates from one basis for a vector space into coordinates with respect to a second basis for the same vector space. And in many applications, and we'll encounter some of these later this semester, such as applications in data science, we'll see that a problem which is initially described in terms of one basis, which might be kind of messy, might be more easily analyzed by changing to a new basis C, where neither of them are necessarily the standard basis. So some properties of bases that we'll see might be nice would be bases where all of the vectors are perpendicular to each other, or bases where all of the vectors in the basis have the same length, and so on. So for now, we're going to think about how I can go from coordinates for our vector space B, which are written with respect to one basis B, which may not be standard, and write these vectors with respect to a different basis for the same vector space, which also might not be standard. So we're going to do this in two steps. And the example that we're going to work with to illustrate how this works is we're going to be working with R2 again with the same basis B that we've worked with earlier, which consists of the vector 2, 1 and the vector minus 6, 1. And then we have another basis for R2 that we'll call C that consists of the vector 5, 3 and a second vector 2, minus 2. And I've got some vector that's written with respect to B coordinates. So the vector 1, 6 relative to B coordinates, recall, is equal to 1 times the first basis vector in basis B plus 6 times the second vector in basis B. So I want to go from B coordinates directly into C coordinates. So the first step might be, since I know how to map from B coordinates into the standard basis, and I know how to map from the standard basis into C, then we'll do this in two steps. So first, we're going to map the B coordinates to the standard basis, again, by taking 1 times the first basis vector plus 6 times the second basis vector. And this calculation we can express more concisely with the matrix product, where we take the change of coordinates matrix, which has first column 2, 1, and second column minus 6, 1. We multiply this matrix, we apply it to the vector 1, 6 relative to basis B, and we wind up with the vector minus 34, 7, which is written in standard basis coordinates. So in other words, this is literally the vector, which is 34 units to the left and 7 units up. So far we've got a basis B and we have a basis C. And what I've done is taken this basis B and mapped it up to Rn in the standard coordinates by applying this matrix, change of coordinates matrix P of B, where the column vectors of our matrix are the column vectors in our basis. And then our next step is going to be to go ahead and map from Rn with respect to the standard basis back into Rn with respect to basis C. And to perform this, we apply the inverse of the change of coordinate matrix for C, for basis C. So the second stage is going to be to then map from the standard basis down into the coordinates relative to basis C. And so the change of coordinate matrix from C to the standard basis, matrix P sub C, right, would have one column, the first column, 5, 3, and the second column would be 2, minus 2. So this is how we go from C coordinates to the standard basis. And so to go from the standard basis to C coordinates, we find the inverse matrix. So in this case, the inverse matrix that we get, that is given below as this matrix minus 16 times a matrix whose first column is minus 2, minus 3, and second column is minus 2, 5. And then we apply this map from the standard basis which maps us into C coordinates, we apply this to the vector that we found in Rn with standard coordinates. So over here, we found that 1, 6 with respect to B coordinates is equal to the vector minus 34, 7 with respect to the standard basis, which is equal to the vector minus 27 eighths minus 137 over 16. And this is written with respect to C coordinates. And to summarize the results from the previous slide, if we've got V is a vector space R2, and we have these same two bases B and C that we discussed on the previous slide, then we found that we can go from B coordinates to standard coordinates by multiplying by the change of coordinate matrix P sub B. So this means we would take 1 times 2, 1 plus 6 times the second basis vector minus 6, 1. And that put us at the vector minus 34, 7, which is with respect to standard basis. And then we found C coordinates of this vector, which is written with respect to standard coordinates by applying the inverse change of coordinate matrix P of C. So we found the matrix P sub C, and then we inverted it. And that gave us C coordinates of minus 27 over 8, minus 30, 137 over 16. So this means if I want to get minus 34, 7 by taking linear combinations of basis vectors in C, then that means I'm going to weight the first one by minus 27 over 8. So I'm going to take that scalar times the first basis vector 5, 3, and then add to that the second weight, which is minus 137 over 16 times the second basis vector. And if you add up this linear combination, we get minus 34, 7 again. So we've just found 3 different ways of expressing the same vector in R2. So we normally would think about that vector in terms of minus 34, 7. We'll see that there will be instances where it might be more convenient to work with a non-standard basis, and then it's going to be useful to know what linear combination of those non-standard basis vectors do we need in order to get back this vector minus 34, 7 that we have in standard basis.